Hi everyone. I'm Xinsun. From Linköping University, Sweden, and now I will present my paper, a large language model approach to classify flakiness in C++ projects. So First, here's the overview of my presentation. I will start with the introduction and explain the motivation behind our research and the specific research questions. Then I will provide some background on Flaky tests and the root causes of Flaky tests, followed by the most related paper in this field. And after that, I will walk through my methodology, including how we constructed our dataset and using ChatGPT-4. And then I will introduce the experimental setup we used for the model fine-tuning and evaluation. Finally, I will present our primary results and the conclusion and takeaways. Yeah, so let's start with motivation. In software development, regression testing is a very crucial activity. Whenever developers introduce new code to a project or a software system, regression testing helps to ensure these changes do not disrupt existing functionality. So this is typically done through automated test suites, which act as a safety net. However, not all test failures indicate real problems. Sometimes tests fail or pass in a non-deterministic way, even though the codebase itself hasn't changed. These are known as the flaky tests. Flaky tests are problematic for several reasons. First, they can make CI/CD pipelines unreliable, so the teams can cannot be sure if a failure is a real problem or just due to test instability. Developers also they may waste significant time to like rerunning these test cases, trying to isolate the root cause of the failure. And over time, this erodes confidence in the test suites, sometimes leading teams to ignore the failures, which is very risky in software testing. In short, flaky tests create noise and confusion, undermining the whole purpose of automated testing. Now, uh, addressing flaky tests typically involves two main tasks: detecting which tests are flaky and classify the root causes of their flakiness. So existing research and tools have made good progress on both detection and diagnosis, but with a strong focus on programming languages like Java and Python. So for C++ remains underexplored despite being a widely used language, especially in performance critical and some legacy systems. So in our study, we found that there is no public dataset for classifying flaky tests in C++, and there are very few methods specifically address this context. So our goal in this paper is to fill the gap, to build a C++ flaky test dataset, and then use large language models to classify the root causes of flakiness in this C++ code. So regarding this goal, we have two research questions. The first one, how accurately can large language models classify flakiness categories of C++ projects compared to Java datasets? The second one, how does the proposed approach compare to previous work? For example, Flaky Cat for Java Flaky test classification. So, what are the root causes of flaky tests? Here is the common root causes defined by existing studies. First, ice weight. The flakiness was caused by asynchronous cores without proper synchronization and concurrency, which is caused by multi-threaded code, which can cause the non-deterministic results if not carefully managed. And then time, like this flaky test usually means they depend on the system time, and this can be unpredictable. And also floating point operation. It's minor differences in floating point calculations might cause occasional failures. And test order dependency. The outcome of a test depends on the order in which tests are run. Also, there are other root causes which are include randomness, networks, resource leaks, and path dependencies. They are not very common, but you can also see some of them in the flaky test cases. So, several tools and research works have addressed the classification of flaky test root causes, but again, most of them focus on Java and Python. For example, Flaky Cat it uses the CodeBird, which is a pre-trained transform model for code, to classify flakiness in Java projects. Other works have used models like CodeBird and Unix code, which can provide not just a classification, but also suggestions for fixing flaky tests. However, there's very little work focused on C++. So our work extends the state of the art by creating the first dataset for C++ and the flaky test classification, and also benchmarking large language models on this task. So with this gap in mind, we set out to construct our own dataset for flaky tests classification in C++. First, we searched GitHub for issues tagged as C++ flaky test, and then manually filtered those tests to remove or duplicates, irrelevant cases, and close the issues. The last, uh, the last step, remove closed issues is very important. So then we can ensure like to avoid possible data leakage, since these closed issues might have their code publicly discussed or fixed, and also they can be included in the training dataset of those large language models. So we then manually categorize the each issue according to the root causes described earlier. And yeah, this process was time consuming but crucial for creating a high quality and a useful dataset. So, however, even after this process, our dataset was still quite small. To address this, we also used a hybrid data augmentation approach. we combined the SMART method and GPT-4. SMART is a statistical method for oversampling minority classes, and GPT-4, as we know, it's a very powerful large language models. So rather than just randomizing the variable names as the traditional SMART method does, we carefully designed the prompt for GPT-4 and use it to change and promote it to change the variable names, constants, and insert unused variables into the original code while preserving the original logic. And for each original test case, we generated five new samples using GPT-4 and then manually checked uh, this to ensure they were realistic and ensure the diversity. This allowed us to create a more balanced and large datasets for training and evaluation. So here you see an example of the original test case and one of its augmented versions. In the above is the original one, and in the bottom is the augmented one. The overall structure and the purpose of the code remains the same, but you can notice that the function names has changed from job func to task function, and an unusable variable has been added. So this approach increases data diversity and helping our models generalize better. So also besides the C++ dataset, we also used the Java dataset from Flaky Cat to evaluate the performance of large language models on Java dataset. So our final dataset contains uh, 362 C++ Flaky tests and 1000 and 1287 Java Flaky tests. Compared to the Java datasets, the C++ datasets has less categories. This is because we didn't find projects containing those categories on GitHub, and so also we filtered the categories with less than 15 flaky tests in the Java dataset to reduce the possible bias caused by the small categories during the fine-tuning. Now let's talk about the models we used and how we trained them. So in this study, we chose three large language models, which are Llama 2, CodeLlama, and Mistral. The size of them are all 7b. So for efficient fine-tuning, we use low-rank adaptation, which reduce the resource requirements and speeds up the training because we have a small GPU. So yeah, and also we use a standard 75% and 25% split for training and testing. It's the same as the setup used in Flaky Cat, so that our results would be directly comparable with them. All the models were trained for 10 epochs with constant hyperparameters, batch size 8, max sequence length 5 and 12, and learning rate yeah. So to evaluate the performance of our classifier, we use several standard evaluation metrics, including precision, recall, F1 score, and accuracy. Since our datasets have imbalanced categories, so the F1 score is a primary metric for evaluation, and also we use the weighted averaging, which is better for imbalanced dataset. So and also the model, the performance was evaluated after every training epoch. Then the result. Here we show the best performance of the three models on two datasets. The Mistral model outperforms the other two models on C++ datasets, and it achieved a perfect score. Llama 2 is better in classifying flakiness in Java. However, CodeLlama gets unexpected results. It only gets a F1 score of 0.79. We discussed the reason of the results. One possible explanation is that the Mistral model, its training data may have included a large proportion of C++ code, which enhanced its performance on C++ datasets. In contrast, the CodeLlama model was trained in multiple programming languages to offer intelligent suggestions and completions. This could explain why the Mistral model performed better in understanding C++ code. Furthermore, the differences in syntax and semantic rules between C++ and Java might also explain the variations in our results. Additionally, the performance of the Llama model and the CodeLlama model also remind us that even for those code specialized models like CodeLlama, they may not exhibit better uh, capabilities than their base models in some of the tasks. So the comparison between our results and the Flaky Cat shows that using LLMs can also improve the classification performance of flakiness, providing a potential solution to this or for this issue. So let's discuss why we see these differences. First, the model's pre-training pre-training data plays a major role. For example, Mistral might have benefit from the C++ code or beta generalization capabilities. And second one, specialization is not always a guarantee of better performance. In our case, CodeLlama didn't surpass Llama 2, so it's possibly due to the trade-offs in its training objectives. So yeah, and I would like to conclude our work and also some takeaways of the study. Based on the results, we can conclude that it's true that LLMs can effectively classify flakiness in both C++ and Java code, and also the performance is better than the previous codeboard-based solutions. So, moreover, we have the following takeaways. First one is, as I said, the different performance between Mistral and Llama models shows that model specialization matters during the different tasks. So it is important to select the proper models for different tasks, which can achieve better performance. And also, this code specialized fine-tuning may cause actually may cause a performance decrease on some tasks, as showed by our result. So finally, we present some limitations of the study. First is the size of the dataset. Although we constructed the C++ Flaky Test dataset, but the dataset itself is still relatively small, like which may impact the generalizability of our results, and it may not cover all real-world scenarios. And also the second one, the data leakage of the dataset. So um, there is a risk of train test leakage if augmented data isn't carefully managed. So future work should investigate more robust splitting strategies. And finally, the model may out of date. Like large language models and code models are evolving rapidly. What is state of the art today may be outperformed by a new model tomorrow. So yeah, continuous benchmarking will be needed in the future. So yeah, thanks for your attention.